Yeah, so first of all, I just want to say I'm really thrilled about the interest and turnout. Thrilled to be here in Australia and at Australian National University, which is such a top institution. And you know, I asked Fader if I could go first because following me is John Stachurski and Bertel, and they're really hard acts to follow. So I'd rather go first because you know, I look bad in comparison, but I'm going to focus today on static structural models to try to start out slow. And, you know, I'm talking about my thesis advisor, who is Daniel McFadden. We're going to talk about the discrete choice model, Daniel McFadden. And, you know, when I was a grad student at MIT, I got my PhD in 1983. And I was studying under McFadden, learning about, you know, he was doing mostly static discrete choice. But then we would have these lectures by Tom Sargent, who is a collaborator with John Stachurski and the QuantEcon. They are the co-founders of that. So it's really a great institution. And Tom was come to MIT to talk about dynamic linear quadratic models. He was working with Lars Hansen at the time, and it was so cool. And the way Sargent would talk, he would give a lecture to students, and then it would be like he was letting you in on he'd say, let me show you how we rig these models. And you really felt like, wow, you're really getting an insight. And he was telling you not only the pros, but the cons and some of the difficulties, the challenges. And then I really got interested in this dynamics. And it turned out at MIT, there's a really, in the engineering school, this guy named Dimitri Bertsikis. And I took a course from Dimitri Bertsikis. And so then, you know, there's Tom Sargent, there's Bertsikis, dynamic programming, Daniel McFadden, discrete, and it's kind of like you have an axle and a wheel and the basket, you put them together and you got a chariot. And then you put them all together and you start driving around in that chariot. So that's kind of how things are going when you think about ideas, putting ideas together, forming connections, and going from there. And these can be very, very productive. So we try to kind of show you this. But what I want to point out is, though we're focusing on dynamics and games today and doing this week, there's a lot of really frontline research in just static discrete choice still. And we were at a conference in Copenhagen, Bertel's colleague Måns Foskerau, and they call perturbed utility models. And they are doing some really, really cool things in static estimation. And we're going to try to give you a little, you know, we put some articles in that area, and we're going to try to expose you to that too. But we're going to start slow. And for those of you who haven't had any exposure, I'm going to just try to say what is structural estimation. Now, where's the lecture one? Here we go. Okay. And then is this clicker? Is this plugged in? Okay. So how many people have heard of this term structural estimation before? No, those, you know, a lot of the faculty, but how many people haven't really been exposed to this? Okay, almost nobody. Almost nobody hasn't been exposed to it. That's good. That's good. Yeah. So we can go a little bit faster through this, but you know, first of all, econometrics, and you can think of econometrics as a branch of statistics focused on economic measurement and prediction and testing of economic theories. And so, as far as I can see, the term structural arose in the 1940s and is credited to a guy named Havemo in Norway, Nobel Prize winner, and Charlene Koopmans and Marchak, and other founding fathers of this area that were at the Coles Commission at Yale. So the Coles Commission started out at Chicago, but there was a lot of hostility to this structure for some reason. There were people just thought this is really not appropriate, that we should just be looking at data. We don't need theory. Theory is just a distraction. And eventually the conflict became so big that they moved from Chicago and reestablished at Yale with a very strong connection to theory. So I think that's, to me, is the hallmark of structural econometrics, is it's trying to bridge measurement and theory. And there's a really great book called by a monograph by Ken Wolpen, one of the leaders in this area, called The Limits of Inference Without Theory, right? And that kind of encapsulates is that we're better when we combine theory and data than when we just do one or the other. And that's what we're trying to do, is trying to bring data together with theory. So I'll just show you a picture of this, here's some of the people. I always like to see some pictures of the founding fathers. You know, it's like seeing George Washington or something. Here's Habermas. I actually met Habermas. I was at the University of Oslo a long time ago when he was still alive, and there was a lecture by Dale Jorgensen, who was a professor at Harvard. He actually passed away recently. And Habermas was a very, very shy guy, apparently. And when he got his Nobel Prize, there were all these reporters outside his house, and he didn't want to even come to the door to acknowledge it. His wife had to kind of drag him out to speak to the reporters. But he was a very retiring guy, but a very interesting guy. And then this is Jacob Martek. So, you know, basically we can think about this as going back to Kant, right? You know, there was the Critique of Pure Reason, famous book by Immanuel Kant, and it was in response to Descartes, which is cogito ergo sum, right? I can know nothing about the real world except that I exist, but everything else could be an illusion, it could be a dream. And Kant was really trying to say that's too agnostic. You know, we can really learn more by observing the world. And that, yeah, sure, there are illusions and things, but we can break through that, and science has a really big role. And we have to use theory and observations and bootstrap our way through the world. And so then I mentioned the limits to inference without theory. Now, I wrote a comment on this in a review of this. So I'm very, very positive on this, but my title of my review, and I have it among the readings, is the limits of inference with theory. Okay, so Ken's was without theory. Yeah, there are limits, but even when you use theory, I mentioned a lot of challenges, and these are the challenges that hopefully we can expose to you that you'll try to overcome. But one of them we're going to talk about, and John will talk about in his lecture, is the curse of dimensionality. Is that when we try to use dynamic programming to solve models, that there's just an exponential explosion in the amount of computation to solve this. Now, there's some really promising areas of ways to kind of, quote, break the curse of dimensionality, like randomization, and some evidence that things like deep neural networks can allow us to break the curse of dimensionality. And this is why we've seen this explosion in artificial intelligence and deep learning, that companies like Google, where they're producing chess players that are better than anyone else in the world, that kind of learn by themselves, by playing themselves and bootstrap and become amazing performers in games and other things. So there's some really, really exciting things. And we say that there's a lot of interest also now in machine learning and structural econometrics, and cross-fertilizing these fields. We talk about reinforcement learning, and I think we'll be touching on this week, where there's some really exciting interfaces between what the computer scientists and the engineers are doing in machine learning and what we're doing as economists. But if you want to say what is so we have another article that Bertel, Fader, and I wrote in the Econometrics journal that compares and contrasts machine learning AI literature to structural econometrics. And we see there's a lot of fertile ground. But a big fundamental difference is that what we do as economists is we're really trying to learn about the world. We're using these tools to kind of understand what people and firms are doing. Whereas the engineers are often just have a goal that I want to predict something well, I want to beat a player at chess, right? So they're using these tools in a very practical way, which is really, really useful and good. But we're trying to use the tools to also try to better understand the world. And the question is, can we use both of them and together and improve our understanding? That will also feed back into the machine learning. So I'm going to, well, the way I want to talk about another hero of mine who recently passed away is Edward Prescott. And I was, when I was an assistant professor, I got to visit Minnesota, and there was Chris Sims was there, Tom Sargent was there, and then there's this guy named Ed Prescott. And, you know, Ed is just a really interesting guy. How many people have heard of Ed Prescott before? He's macro. And the first time I met Ed, so I'm more micro, but I was in what's called the Management and Economics Tower at University of Minnesota in Minneapolis, and there was this guy standing in the doorway. I had this foot locker from my dad's Marine foot. It was full of books, and I was putting them in the shelves because I was going to be staying there for the entire semester. And there was this guy who was arms folded, and he kind of slightly balding. He was wearing blue jeans, tennis shoes, a polo. He looked kind of like a soccer player. I didn't know who Ed Prescott. It was, you know, it turned out to be Ed Prescott, and he was kind of glaring at me. And I reached out my hand. I was going to shake his hand, and he wouldn't shake my hand. And I'm thinking, well, okay, whatever. So then I reach in and I start putting more books on the shelf, and he's just staring at me. And then finally, I put a book called Econometrics by Henry Tile, and I put it on the shelf. I reached out for some more, and then the next thing I know is Ed pulled that tile off the shelf, and he's kind of paging through it. And the next thing I know, I look at it, and he takes both ends of the book. It's a red book. It was kind of already decaying a little bit, and he was like using it as a fan. I was worried it was going to split right down the spine, and he slammed it shut and threw it into the wastebasket, and he said, "You read that crap?" And then he walked down the hall, you know. So Ed had an antipathy to econometrics, and you know the question is, why does it? You know, so he promoted something different than econometrics, which was he called calibration, and his students are almost like a tribe. And you know, in Minnesota they have the French motto, liberté, égalité, fraternité. Well, the Minnesota model is optimalité, equilibrité, calibrité. Okay, it's basically similar to what our model is, except you know we do take econometrics seriously, but calibration is kind of a way of fitting models to the data informally. But they don't worry about standard errors, and they say, well, we'll take this paper from Sargent, we'll take this from Manueli, and we'll take the discount, we'll set the discount rate to 0.95, and then we'll choose these other parameters that we can't find from other journal articles to try to make the prediction of the model as close to the data in some informal metric, and then put them together, right? So, you know, that's what we're trying to do in econometrics, but we also say, you know, what are the properties of our estimators? What do they have standard errors? Are they consistent, right? And what is the best metric that we should use? Should we use the likelihood? Should we use generalized method of moments, simulated method of moments? So we take the method of estimation more seriously, but I'm not going to hold that against Ed Prescott, right? Fundamentally, what I really admire about Ed is he cared about theory, he cared about confronting theory to data, and he was tremendously successful and influential in doing that. So I'd say he is you know, another one of my heroes in this area. So, you know, we might first talk about what is a model. And if you look at Wolpen's monograph, it didn't define what a model is. And Tom Sargent has a definition of model, which I think is a little too, I don't know, it's not meaty enough, but he says a model is a probability distribution over a sequence of vectors, usually indexed by some fixed parameters, right? So if you listen to that, do you know what that means, John? You're nodding your head and smiling. You know, what does that mean to you, right?
says that all the time. I teach the class. First thing he says, yeah, it's classic Tom, isn't it? And he likes this sequential approach to economics, whereas a lot of people are talking about things recursively. But yeah, it's kind of like it doesn't give us a huge amount of content yet, does it?
Yeah, no, for instance, you might say the regression is a model, right? There's some prime beta and there's an error term and a Y. But a lot of us in instructional economics say that's like a reduced form model, right? There's no theory, or oftentimes there's no theory. Sometimes theories lead to a regression specification, then we say that's a model. But we want to be agnostic like Tom Sargent. We don't want to say that structural models are the only models. There's a whole work, most recent Nobel Prize or a year ago, David Card and Josh Angrist, their work on causality. And if you think about the treatment effects model, that's a model, right? And they're really interested in trying to learn causality. And we are really interested in that in structural econometrics too, except we're also interested in the decision-making of firms, and we want to go beyond the causality. That's part of our models. We need causality and a belief about causality that also to model how firms then, for instance, causal is, what's the effect of raising the price on my demand? There's a causal relationship, but we just don't want to know the demand curve. We want to then say, is the firm setting the price optimally? Are they doing price discrimination, right? And how do firms interact in equilibrium? Is it a Cournot or a Bertrand equilibrium? And we look at these strategic interactions. So we're not just stopping at the causal, but that's often doing that right is very, very important. So those guys do models. Now, personally, I don't really get treatment effect models. When I look at them, they're opaque, they don't talk to me. Structural models will talk to me. I understand because I understand the economics, and going from the economics to the model to the data, for me, enables me to kind of live. Otherwise, some of these models are too abstract, they're too statistical, I don't get them. But that's my problem, right? And I say that's not a model or that's wrong. I don't want to say that. I think that people think differently. And there's people like James Heckman, another hero of mine. He works in both of these worlds, made tremendous contribution in the treatment effects literature and also in the literature on structural estimation. And he can go back and forth. And the people who can go back and forth, that's an incredibly strong skill. So I'd like to, basically endorse that. And also this parent, there's always been a view that there's been hostility between reduced form econometrics and structural econometrics. And I would say, let's not go there. Let's say that when we do empirical, we want to start out with reduced form. We want to kind of not put too much theory and see what's going on in the real world with non-parametric things to describe the data without trying to put blinders on our eyes to a particular model, and then look back and say, what is the best model that's off the shelf, or do we need to build a new model to describe what we're doing, right? So sometimes we look at theory and we're trying to test an existing theory, but sometimes it's really exciting about what we do in structural econometrics is that we find out there's no good theory for the data we're looking at, and then we become theorists and we invent the theory to explain the data. And that's, for me, that's really, really fun. So I wouldn't be doing theory without a context. So when I look at data and then I see puzzles and then I try to build a theory to explain it, to me, that's really, really fun and really very productive. So the other thing is, when I mention structural econometrics, you often think, well, that's also part of it is rationality, equilibrium. So, equilibrite, optimality, right? That's the Minnesota part. But I would say in structural econometrics, I would put equilibrium with a question mark and optimality with a question mark. These are hypotheses that are very, very powerful if we impose equilibrium and optimality, rationality. But sometimes our models are impossibly demanding to the point where a lot of us can't even solve our own models. We write down models, and when we say, holy cow, we have to solve this model, we just say, hey, I don't know how to do it. They're too difficult for us to solve. And then it may start to be bizarre, because if we are saying people are solving these really difficult problems that we can't solve, the question is, are we asking too much? Now, there's this notion of as-if optimality. Milton Friedman at Chicago pushed this line, right? He said, you could be an expert pool player. When you're an expert pool player, there's a lot of physics, right? The angle of incidence equals the angle of reflection. M times V equals F times T. Angular momentum with spin, right? And a pool player will learn physics without even knowing they've done it by trial and error. So it could be that humans, their brains, our neural nets are so powerful that we learn to behave according to theories without being consciously aware of doing it. And that somehow our brains are so much more powerful, right? So, and I'm a big believer in this as-if rationality, because so far, even though AI has progressed tremendously, I have some articles about the energy efficiency and power of the human brain. Apparently, you can measure physiologically, our brain takes about 20 watts of energy. But if you measure in terms of the number of calculations, our neurons are really, really slow, but there's thousands of connections and pathways and branches in the neural net of our brain. And it uses very little energy, but it produces calculations that could be equivalent, you call petaflops. Petaflops is like 10 to the 18th operations per second. Now, the computers we have now that can produce at the petaflop level, they use as much energy as a small city, probably as big as Canberra, to run this computer, right? So there's something about nature that has produced, and the thing is that our ability to adapt to so many unexpected situations is just incomparable. When we write a computer program, it's a very narrow thing that can do things well, like play chess, but it can't get up in the morning and make coffee and figure out how to get to the bus and recognize a friend and do all the things that we do, right? So when you think about what we do, it's truly, truly amazing. And what I'm going to be promoting, and I'm really interested in an area called neuroeconomics and neuroscience, is that how do our brains do this, right? So I think there's a really interesting area about trying to understand our brain and mental process, and how with so little energy we can be so smart and do what we do. Now, we may not be as smart as a computer in a very narrow domain, but as a broad domain of sensible intelligence, we are amazing, right? And we don't really understand how, I don't think anybody, neuroscientists or anybody, knows how we do this as well as we do. Now, anyway, that leads me to, we may not, because of our broad IQ, broad intelligence, we may not be narrowly optimal in certain tasks. Nature, when you think about evolution is, tells us we should be good in lots of things because nature throws a lot of things at us. But to be, nature wouldn't have evolved us to be great at chess. It's an artificial human game. And so if the computers are outperforming us, it shouldn't necessarily say, wow, people are stupid. But on the other hand, it's probably not surprising if we build very narrow rational models, we're going to reject human behavior as being optimal or falling into equilibrium in many cases. And that leads to behavioral economics, right? Behavioral economics is trying to relax just very strong rationality. And later in this summer school, I'll be talking about auctions, which are really hard things, dynamic auctions, and work with Harry Parsh and my co-author Sung-Jin Cho, where the most demanding notion of equilibrium is called perfect Bayesian equilibrium. And the kind of calculations you have to do to follow a perfect Bayesian equilibrium in bid is again, it's a game that nobody can solve. Nobody knows how to solve that game. But if we back off of rationality a little bit, so the line I would push is try to start with rationality. It's a very reasonable starting as if we can't solve the model, then what's the smallest relaxation of rationality where we can get models that we can solve and then let's say, how well do those predict human behavior? So I think rationality is a really good starting place, but I'm very friendly to what behavioral economics, so I'm very friendly to Stefano Della Vigna's Handbook of Behavioral Economics chapter called Structural Behavioral Economics. And I'll try to get that article and put it on the reading list as well. Now, the other, maybe the main reason is something called, how many people have heard of the Lucas critique before? Okay, yeah, this is well known in macro, and it came about in the basically Lawrence Klein, another notable. I was a student in undergrad at Penn, and there was Lawrence Klein, and he built these macro models, and they were trying to use these macro models to forecast the economy. They weren't kind of completely behavioral models. They were just a lot of regression, simultaneous equation system, dynamic systems. And what they found is these systems were unstable. When they tried to fit them, they would work for a few years, but then they get some more data, and then they would re-estimate. The coefficients were kind of always drifting. So the models didn't have a stochastic structure that was stable over time, so they would become unreliable in forecasting. And Lucas observed that and said, well, the reason is you're not doing structural models. You should be going from first principles and looking at the fundamental parameters, which are people's preferences, and what he would call structural, and production parameters like production functions. And if you can identify the production preferences parameters, the preference parameters, and then also separate those from policy parameters like the Federal Reserve's control of the money supply and interest rates, and then say there's policy parameters, there's preference parameters and production parameters, and solve models where you separate these out. Those models then are possible to do what are called counterfactual predictions, that you can now show if you change monetary policy in a certain way, how will it that may be deviating, there's no past experience. We can use these models to simulate, because we think that monetary policy change is not going to change preferences or production parameters, right? So that was a really great rationale for why you want to do structure, why you want to do all this work. It's counterfactual predictions, and you're going to see that this entire week is a typical structural paper will be get data, identify the structure, estimate those structural parameters, and then use that model to make counterfactual predictions. Okay. Now, it sounds really beautiful, but in my critique, or not a critique, but basically an admission of some of the challenges we face in structural econometrics, is that you might say our preferences really structural, right? Like, for instance, do you have the same utility function as you did when you were a 6-month-old baby? Probably not. And I'm a 67-year-old man. I'm different than when I was 35 years old. And so there's drift in my preferences that are changing over time, and our production technology is invariant. No, there's technological change that is dramatically changing the production network. So, when you try to look at what is really invariant, it's really hard, if you really push it, to say, is there anything? So things are maybe only locally invariant, and maybe they're kind of invariant within a limited class of counterfactuals. But it really can turn Lucas back on himself. He was criticizing Lawrence Klein. They were re-estimating these models. Oftentimes, when we estimate these structural models, we find they're kind of good for a little while, but then suddenly they become irrelevant because technology changed, new markets and firms that come in, and now our model just doesn't apply anymore. So, that's a huge, huge challenge. So, yes, Lucas was right. In a stationary world, this, looking for structural invariance is what you want to do. But it's more challenging when you acknowledge that the world is really fundamentally non-stationary, and how do we predict this future, right? And so finally, another critique I would say is you're going to see in a lot of the work we're doing is we're adopting a stationary infinite horizon model, right? But is the world really stationary, right? We're using this, the future is like the idea with a discount factor, something way off in the future is kind of negligible, but really, we don't really think we can predict 50 years out, right? It's really heroic to think we can predict 50. There's a book I really like by a guy named Ray Kurzweil. It's called The Singularity is Near. And the singularity is, how many people have heard of this book, Singularity is Near? It's a very cool book. I recommend, I was looking at John's, he's got his favorite books. It's one of my favorite books. And Kurzweil shows that technology is speeding up and it's accelerating. And the singularities, he predicts it to occur around 2054, is where the rate of technological change is so fast that it becomes essentially infinite, and that we can't predict what the world's going to be like. It's like going into a black hole. We don't know what happens on the other side of the black hole. So beyond 2054, according to Kurzweil, things are going to be so radically different that we just won't be able to predict the world. And that the nature of technological innovation is fundamentally unpredictable, and nobody really can predict its evolution with any degree of accuracy very far out. So that's a challenge. Like when we model, how do we model the future when there's these huge non-stationarities that creates a huge area for research in a technologically evolving economy, right? So, we're on the verge now of quantum computers, right? What will quantum, I see the other day, fusion power, right? They've got now in the US, they're about to announce the first fusion reaction that will produce more net power than it takes for the lasers to constrain the fusion reaction. And that's a game changer, right? If you think about CO2 emissions in the planet, if we can make successful unlimited amounts of fusion power eventually, think about that technology, what that will do to life on planet Earth. And I don't even go there about biological engineering and, questions like, are humans the end of the evolutionary ladder, right? Anyway, I'm going off structure, but let's talk about this. So let's be a little bit. How am I doing for time? I'm 39 minutes. So here's one of the classic models in the Coles Commission can be written by these equations. And it's the linear simultaneous equation system. We rarely teach it. Does anyone teach? Any of you guys teach that in econometrics anymore? Well, we got it when I was a grad student, right? I had Frank Fisher, and we learned about the rank and order conditions, and we had to learn about, and then we learned all about it, and then we promptly forgot about it, right? But you can see these different equations here, and this is why when you endogenous variables, x will be exogenous, either vector coefficient. So this is an either error field. And there was something called the structure. So if you look at the equations for equating supply and demand in multiple markets, you would get this equation here. But then if this matrix of coefficients was invertible, you left multiply by its inverse, and you would get something called the reduced form, right? The reduced form predicts y as a function of independent variables or exogenous variables and a modified disturbance term. And the idea is the reduced form is like a system of regressions. So you could just go out there and do regressions and then get the pi coefficients and potentially the covariance matrix of the residual, right? That there's a covariance matrix of the u's, which is sigma, and then when you close multiply by gamma inverse, you would get this. So the question is, if I can identify the covariance matrix from the regression, I can identify the pi. Can I go backwards? And so I observe this, I can identify this and this from regression. From those, can I invert and get the structural, the sigma, the b coefficients, and the gamma coefficients, right? And that was called the identification problem. And when can I go from reduced form, without making any extra assumptions, to go to the structure? Okay, now does anyone know the answer? Is it in general, is that invert pattern? It's something that looks like it can't be identified because there's three of these things and there's only, you know, if you just say, well, in a very crude sense, there's two of these, there's omega and pi, yet there's actually three of these things. So is that, do you think is this identified? In other words, can I invert uniquely, get all three of those structural things from the two reduced form things? Does anyone want, you know, anybody want to hazard a guess? Well, the answer is that in general, it's not identified. In other words, multiple structures, we call it observation equivalent. We can find multiple structures consistent with the same pi and the same omega. That means we can't tell those two structures apart. And the way they showed this in a very intuitive way is that if you look at just a single supply and demand, you know, basically we have shifting demand curves and supply curves. And when we see a market equilibrium, it's the intersection of supply and demand, right? And if you can imagine if the supply and demand curves are shifting all around, the data is a bunch of scatter plots. And oftentimes when you look at a scatter plots of supply and demand combinations, it's a big circle. And then you say, well, if I fit a regression, will it be a demand, will it be down sloping? Will it be upward slope? It could be any of the above. And so how could I identify both the slope of the demand curve, which is downward sloping, and the supply curve if I only have these supply demand intersections, right? So how do I identify? So does anybody know how we make progress here? What will we do then? You know, until we just throw our hands up and say we can't do anything, or what will we do if we're fronted with that problem? What did the elders do at the Coles Commission? Does anyone want to know? The people who already know the answer to this, but some of the students, does anyone want to make a guess or say which guess?
Find a shock that affects on the model.
Very good. Now, so this is called an exclusion restriction. Some X variable that shifts just the demand curve, but not supply curve, or vice versa, right? Like if you look at agricultural commodities like rain, right? Australia is getting a lot of rain, and that's shifting now. I've heard there's going to be a lot of vegetable production in Australia because there's lots of rain. Now, if you believe that rain doesn't cause people to go out and eat more, then what you're doing is, if you see looking over years, the supply is shifting because there's drought to lots of rain, then the supply curve is shifting over a relatively less shifting demand curve, and that can be used as what's called an instrumental variable to identify a downward sloping demand curve. Okay, and then vice versa, you can identify the supply curve if you can see something affects demand that doesn't affect supply. So these are called exclusion restrictions. They're X's that enter supply but not demand, and other X's that enter demand but not supply. And when you have enough of these exclusion restrictions, you can identify the parameters. There are extra information or prior restrictions that you make. And then in these cases, we can think of the X's as being instrumental variables. There are variables that shift one thing. And basically the literature on instrumental variables came out of this structural work at the Coles Commission to identify supply and demand. Now, I'm saying this just as a very simple example, intuition. I don't say you need to go and study this, but is it relevant? It's still relevant. I just got back from a conference. Some of us went that Nick Ruse hosted, and the keynote speaker was John Asker. John Asker is a product of this city, right? A famous graduate of Australian National University, and he was talking about OPEC and the cartel, the oil cartel. And in his model, he had a linear aggregate demand curve for crude oil. And he was talking about OPEC, but then a residual, basically competitive fringe of companies that are not in OPEC that produce a residual supply that leads to kind of a flat part of a low marginal cost and then a rising marginal cost of less efficient fringe producers. And he used assumptions about cost shocks to the fringe producers to show that that was an instrumental variable that he could identify. So he showed in his lecture a beautiful picture showing price and quantity diagram where you would have gotten an upward sloping demand. If you just treated those as demand, it would have been upward sloping, clearly the wrong side. And when he used his instrumental variable procedure, he got a reasonably sloped, downward sloping demand for oil, and he could do his really cool analysis of the welfare cost of the OPEC cartel, which is in $6 trillion, right? Something like that. He estimated over from 1970 to 2020 or something like that. So this stuff is actually still relevant. And you know, when John Asker's paper is ready, I will put it in the box because I think it's really cool stuff. It's a static approach, but it's still really insightful. Okay, so I'm going to make some executive decisions now. I want to move to discrete choice because I'm a more micro guy, but I want to try to give a lot of credence to what's happening in macro literature has contributed hugely. And today, what we see is some of my colleagues, it's almost like they're blending. Like I have a colleague named Mark Huggett, and people talk about Huggett style models. They're kind of life cycle models that I can totally relate to. So they're looking at individual models and with micro aggregation to the macro economy. And so in some sense, you know, the gap between micro and macro is starting to disappear. It's starting to, you can go from micro to macro labor, micro labor, and that's a really cool transition that, you know, in some sense, ultimately we'd like to build up the macro economy from micro foundations and aggregation of, you know, models of individual people and firms. In fact, this was a long held goal. I started out my career at the University of Wisconsin, and there was a guy named Guy Orcutt. Did anyone ever hear the name Guy Orcutt? Well, the building that the econ department is called the Social Systems Research Institute. It's a really cool building right on the lake at the University of Wisconsin. And Guy Orcutt got that from an NSF grant, and he was so ambitious. It was in the 1960s, and he talked about social systems. He was trying to do exactly this, to get data on micro individuals, build, you know, micro models, then aggregate them up to kind of build a model of everything, of the entire economy. It just was too ambitious. I mean, he had, I think, the right approach, but you know, the computers at the time, the data was limited, and he couldn't really ultimately deliver. But the testament to Guy Orcutt is that building is still there. So it's still challenging us for us to do it, but we're seeing this transition and this melding between micro and macro. So I think I'm going to, so we can think about a more micro-oriented model. I'm going to talk about the discrete choice, but we think about a class of models like this. Now, we have, again, X variables. We also think of exogenous variables, and then this will be like a choice variable. It could be discrete or continuous. And there are going to be parameters theta and pi. Pi is going to be a policy parameter, and the theta will be the structural parameters of preferences or technology. And the reason, the next thing I want to focus on is why do we have these epsilons in the model? Can't we get rid of the epsilons, and do we need them? And the easiest way to see is that if we, especially in micro data, if you don't have any epsilon there, you get what's called a statistically degenerate model. In other words, if you only see y's and x's, there's going to be no model that's good enough to predict exactly every y. Right? No model there's going to be no value. Pi might be set the policies that were in effect in the data, then try to find a pi that perfectly predicts every y for all the values of x. It's going to be impossible to do. The model will fail. We also, if you're doing maximum likelihood, it's called the zero likelihood. If you evaluate the likelihood, some models will not be rich enough, and you'll find out there's a parameter, and there'll be some people that have zero likelihood. And if you try to maximize that, and the whole likelihood is zero, so you're stuck. So a lot of times what we do is we put this error term into this equation so that we can get some, it has a positive probability of predicting any possible outcome. So that's a non-degenerate statistical model. Okay. Now the question is what's the interpretation of the epsilon when we put this in the model? So, you know, one is we just want to get a language that isn't zero. You want to fit the data, but then what's the interpretation? Now, that's something we have to think a little carefully about, because one interpretation is, well, it's an optimization error, right? So people are trying to optimize, they're trying to behave optimally and do the best thing, but then something makes them do something suboptimal, right? Now you might say that's a little bit crazy. Like if I, I want to retire, but then some, random shock makes me not want to retire. What's the interpretation? Though, just to say that we're doing something optimally all the time, except shocks. Now you could sometimes tell that story. In game theory, there's what's called the trembling hand equilibrium, right? You want to take some action, but your hand trembles. I'll be talking later this week about tennis. And in tennis, right, you want to get it over the net as fast as possible to serve your first ball. But oftentimes top tennis players, they fall, right? They're shooting it as fast as they can. They're not trying to get into that, but something in their control of the muscles is not perfect. So you can say, is it an optimization? It's some shock that their neurons are not fully in control and the ball goes in the net. And then they take a second serve, they back down on the speed and then shoot the second serve in and gets it over the net. So they rarely double fold, right? Double fold is really big, pros really rarely do that, but many pros will often miss the first serve. So you can tell a story of some kind of, you're at the edge of your ability to control yourself, and these epsilons are these random things in your neural system that make you do something else. So we'll also talk about rational inattention, or an idea of Chris Sims. I'll be talking about that later this week. And lapses of attention, right? You just tune out, right? Maybe some of you doing that right now. Yeah, and it's just natural. Our brains just kind of tune out when we think about, brains, a lot of stuff going on. But another interpretation we're going to talk about in dynamic discrete choice is epsilon is an unobserved state variable. Okay, so the idea is that the econometrician observes also what the agent observes with X and Y, but there's other things that affect the agent sees that's inside your brain that the econometrician can't observe, right? There's just lots of things that are going on inside our brain. So it's very plausible that people are doing things with more information than we have as an econometrician, and then that epsilon represents those other factors that affect our outcome that we can't observe. And that's a line that I pushed in my work. Now it seemed very plausible if you'll have that, but we have to make some assumptions about this. A lot of times we assume this epsilon has particular distribution is IID because it's serially correlated. It's just gonna, when we talk about dynamic programming, it's much more difficult when the epsilon is serially correlated, but it can be handled. There's new ways of handling serially correlated, but the initial models we just assume these are transitory shocks. So we try to get all the dynamics in the X variable, and then say whatever's left over is more likely to be IID. But in some ways you could test and reject that assumption, and it is, then you want to actually include what the epsilon is. Okay, and then if the epsilon is serially correlated, you have to integrate out over the entire path of epsilon, and that leads to a humongous multiple integration if you're doing maximum likelihood. So these are, let me just stop here and see if anyone has any questions. So I will go now into more specific. I'm going to skip through, and I'm going to skip a number of slides to keep us on track. So how much time do I have? It's 10 o'clock. I have half an hour more theater. 50 minutes. 15 minutes? 30 minutes. I have all these longer slides, but I'm going to talk a little bit about discrete choice models in the last 30 minutes, and I'm going to do a cover and empirical application, which is a really one of my favorite articles called "Are People Bayesian?" Okay, so it's about learning about how people learn. In fact, now I'm going to go one level further in meta-analysis. I want to say, can we learn about the best way to learn about how people learn? Okay, so that is, how do we model how people are learning? And I'm going to be using experimental data from the, so I'm going to introduce you to the discrete choice model, and then we're going to go through an empirical application where by Eldemala and Grether have a different way of modeling the error terms in the experiment, where it's kind of like randomly flipping the coin versus the McFadden way. I'm a student, so I'm promoting this other way, which is called the random utility model. So the random utility model. So before I go into this, does anyone at this point have any questions? So what we're going to go is now we're going to static discrete choice, my thesis advisor's work, and then give you a little history, and then we'll go to Are People Bayesian in the application. So the McFadden called it RUM, random utility model, and the idea is that you are in some state and you take a decision. There's a deterministic part of the utility, they call it strict utility. And then there's this other error term, which is the unobserved things affecting your choice that we don't observe as combinatorial, that has some probability distribution. So your total choice will depend on X and epsilon. That's called the decision rule. It says that whenever you're in this state, this is the optimal thing to choose. But the problem is that we don't observe epsilon. So if we are going to do estimation by maximum likelihood, we have to integrate out with respect to this distribution of epsilon. Now notice there's an epsilon for every element in the choice set. So the choice set has 10 choices. Epsilon will be a 10-dimensional random vector. If you're looking at cars, there's thousands of cars, hundreds of thousands of cars, right? And if you want to use a random utility model, my wife just bought a car, and she bought this. You have to use car, and she's picking it up today. Well, she could have looked at hundreds of thousands of cars, and if you were to model her choice, then you would have a choice set of hundreds of thousands, and you would have to do the integration here to get what's called the conditional choice probability. So the probability of picking one car, which my wife chose a Ford, given X's, including her characteristics, her age and income and so on, those are variables that affect her utility. Integrating this out would be a really high dimensional integration problem. And one of the lecturers here later this week is Michael Key, and together with John Gawicki and Vasilis Hadjivassiliou, they have the GHK estimator, right? So how many people have heard of GHK before? There's BLP. How many people have heard of BLP, by the way? Okay. Well, GHK, it was a big acronym, but it's the Gawicki Hadjivassiliou Key. It's a very efficient multivariate integration by simulation for getting accurate estimates of the multivariate integral, but by numerical integration, not analytical integration. Okay. But now I'm going to show you a beautiful result of Daniel McFadden, where there's a particular distribution for all these epsilons that could be 10-dimensional, 100,000 dimensional. It's called the extreme value distribution. And when you use extreme value distribution, this choice probability is always an analytic formula. Beautiful, easy to evaluate. It's called the multinomial logit. How many people heard of the multinomial logit before? Yeah. So I'm going to, a lot of people have seen it, and I'm going to show you a derivation. You could, by plugging in the expression for the extreme value, which I'll show you in a minute, do all these integrations by group, if you're really good at math, and sure you go, but there's a much more elegant way using duality theory. And then essentially, there's something called the Williams-Daly-Zachary theorem, and it's like the analog of Roy's identity. If you study microtheory, it's like the discrete choice version of Roy's identity. And there's a whole budding literature now that people like Mons Foscarol and others are using duality theory in these perturbed utility models to really big effect and with really deeper understanding. I'm going to try to give you a little bit of flavor of that, but you can read further in the notes and the readings. I have some articles about this, and there's an article in 2019 Econometrica by Raybeck and Allen that take this idea and extend it to a whole class of models, including matching models and so on. So it's the duality theory. I'm going to give you exposure to it, and by showing you how you derive the multinomial logit model. And further, it's going to show you a fundamental result that Aaron's going to be talking about in Bob Miller, called the Haas-Miller inversion. So when can you invert? If you think about this is the reduced form. It's a conditional probability, so we can estimate this kind of like a non-parametric regression, non-parametric methods to uncover this called the CCP, the conditional choice probability. And when can we go back and invert and uncover the underlying utility? So the Haas-Miller inversion gives us conditions where we can go back from the reduced form and uncover part or all of the structure. And Aaron's going to be showing you about that and how to actually compute and do that inverse math. So, I'm going to quickly go over this, but the logit, McFadden didn't invent the logit model. It was invented by a guy named Duncan Luce, a mathematical psychologist. And he did it axiomatically. He created an axiom called the independence from irrelevant alternatives. And what it says is that you can think of if you have a larger choice set and you're choosing some alternative little b from a larger choice set, you can think about that as first the probability of choosing some subset of the largest choice set. You're going to take something like my wife chose cars. Well, she didn't look at electric vehicles. She just excluded that. She just looked more like SUV kinds of cars. And so she looked at a smaller choice set from the big choice set, and then chose her car from the smaller choice set. So what this says is that you can think of it as the probability is the combination of choosing a subset, a more limited subset, consideration set, and then choosing your alternative from this consideration set. That's the same as choosing your alternative from the overall big set. And when you do that, you get the formula for the multinomial logit model. And so you get that's the formula 5, where these V's are going to be like the utilities of the different alternatives. Now, I wrote it here as V's instead of U's because when John and Beryl come in, we can make some assumptions about the intertemporal correlation of the epsilon. We can extend this to dynamic choice. So now we're going to reinterpret the V as not just today's utility, but the discounted utility from today and tomorrow onward. So we call that the choice-specific value function. V is the choice-specific value function. And in the literature on reinforcement learning and something called Q learning, that's called they call it the Q function. And that's what they learn. They learn the Q function. And I have another reading in there by John Sitsiklis, one of my other professors, and he shows that the convergence of, they can talk about the convergence of Q learning, stochastic updating algorithms using stochastic approximation result. Very cute. It's called asynchronous stochastic approximation. They use that to show that the Q learning algorithm converges to the true value function. Right now, John will be coming back. He'll talk about deterministic algorithms for solving dynamic programming, but they're stochastic algorithms. Ariel Pecos will be talking about that as well. And he's used these ideas in games, learning in games. So here's Duncan Luce. So another way to say the IIA properties, you look at the multinomial logit model, if you look at the odds ratio choosing alternative E versus alternative prime, it only depends on the utilities of those two things, not on anything else. But what's been found is that in many experiments, those other things do make a difference. So in other words, other things besides the things you're considering affect this odds ratio. And so in other words, there's empirical evidence that people don't behave according to the IIA axis. And furthermore, in work by Barry Levinson and Pecos, the IIA algorithm of the property can generate unrealistic patterns of cross elasticities, like for cars. And there's close substitutes and far substitutes, and sometimes it just generates equal cross elasticity when you just don't see that in the data. So the logit model has some strong drawbacks, and a lot of the work is trying to say, how can we overcome the drawbacks of the IIA property? So an example is the red bus, blue bus paradox. So for instance, this was Dubrow did a review of Duncan Lewis's book. And in his review, he came up with this example. So suppose you have, you can either walk to work or you can take a bus. And when you go to the bus stop, it's either a red bus or a blue bus. Now for you, the red bus and blue, they're completely identical. It doesn't matter if it's red or blue, it's just a bus. So, the main decision is, do I take a bus or do I walk? Now, so you're completely indifferent between the blue bus or the red bus. So here I have a car, but if the two utilities are equal, so we do an experiment. Well, here I have a car instead of walking. So the multinomial, if you just had a bus or a car and they're identical, the model is, if you plug it in multinomial logit, it's 50-50. Somebody's going to take a car, somebody's going to take a bus. Now, what he said is, let's now do a counterfactual experiment. So we still have the bus, but now we're going to put colors on those buses. Some are red, some are blue. And the bus comes. Now I'm going to look at this model, and now it's like it's like a fake new alternative. It's just artificial, but do I take the red bus or do I take the blue bus or do I take the car? Well, now you're indifferent between all of these things, and now you have three choices, and you plug that in the logit model, the probability is 1/3. Well, that's not how we would think it would happen. You just say, it's either bus or car, and these other attributes being red or blue is totally irrelevant. So it should be still 50-50. But now with this IIA, it introduces, you get a counterfactual prediction that's manifestly unreasonable. So that's why you should be concerned about the IIA. And so we get computational simplicity, but it comes at a cost. And so that's why Michael Keene and other people, when we talk about random coefficients models, here's a model where you have a utility form of this. XV is a vector of attributes of cars, for instance, car horsepower, styling, acceleration, do they have battery or what kind of fuel? And you can think about a random coefficients model is the utility is you take a weighted average of all these coefficients, but different people have different betas, right? And from our point of view, they're random. What weights you put on those are alternative. Now, if you assume the betas are a normal distribution of mean, mu, and sigma, we have kind of random coefficients heterogeneity, and then we can write the error term this way as a random utility model, where we write the mean, we take the p tilde, and we write as mean plus a residual. And now what we have is an error term, which is heteroscedastic. It depends on the axis. And what this model has is the advantage, and this is probably why Michael Keene and others like the probit model, even though it has no closed-form solution, is that now if two cars are like in very similar in observed characteristics, their choices are going to be perfectly correlated. If you look at the covariance of the variance, that's going to go to 0. So if you have a red bus and a blue bus, and you use this model, you're not going to get unreasonable prediction of the IIA model. So, a lot of work now is trying to take the best of both worlds, called mixed logit. You have a logit model with a little error term there that has IA, but then you have random coefficients on top of it, and the mixture of the two can generate realistic demand patterns. So that's what's going on in IO. So let's go now to something in duality theory. I want to just give you a little exposure to that. It's called the Williams-Daly-Zachary theorem. So you're going to hear a lot about this Emax function. Emax, and it appears even in static discrete choice models. So the Emax is the expected maximum utility. So that's right here. This, if you say there's error terms that are random variables from our point of view, we take the expectation with respect to them. That's the thing here. The Williams-Daly-Zachary theorem say it's like Roy's identity in micro, except there's no increment. It says if we take the derivative of that Emax function with respect to the utility of some alternative, that's equal to the choice probability. Now here's the reason why. The idea is that if you raise the utility of one alternative a little bit, and you think of epsilon as the population of consumers, if you take the derivative inside the integral function, inside the max, which you can do under certain circumstances, when you take the derivative, you get the indicator function. In other words, whenever for any epsilon where this is the max, when I take the derivative, it's just going to equal 1. But for any set of epsilons where it's not the maximum, it's going to be 0. So when I take the derivative inside this integral, I'm getting the indicator function of when it's optimal to choose alternative D. And when I integrate that with respect to all the epsilons, I get the choice probability. And just think about it, it's really an exercise in the Lebesgue dominated convergence theorem, right? Interchanging integration in in derivative. Now, here's the formula for the density, multivariate density of extreme value. And we're going to use this theorem and another trick. The extreme value distribution has a property called max stability. Okay, now think about the normal distribution. Sums of the stable distributions are random variables such as sums of that distribution are in that family. So sums of normals are normal. The extreme value has the property under the operation of max. Maxes of extreme values are extreme values. So if you look at this, here, this is a shifted version of extreme value distribution, like a mean shift. The max means that thing is an extreme value. So the maximum utility is a extreme value. And if you work out what the mean is, the mean of that thing is going to be, here's an extreme value distribution. If you work out what it is, and do the max of random variables is just a product of the marginals if they're independent. So this is the equation here. You can look at it, and you can condense all these individual means into something called I, the inclusive value, which is the Emax function. So I is, and it has a closed form solution here, right there, equation 9. That's the expected max. And so what you would do is, in the discrete choice problem, you would put the utility there. So here, you can work it out. This Emax is going to, this part here is the log sum, but instead of mu, the means are going to be the utilities divided by the scale parameter. And when you just do the calculus, there you go, you get the multinomial logit model. Okay, that's the way you got this. That's a kind of duality way of thinking about it, and is much easier than doing multivariate integrations. Now, what you do to estimate these models is, so the beauty of the extreme value distribution is this model is not statistically general, right? See, exponential is always positive, unless u is going to positive infinity or minus infinity. These probabilities will always be between 0 and 1. So this is great for maximum likelihood estimation. There's always some probability that you see people taking some action, no matter how crazy, right? I can run and jump out the window, and the illusion model is going to say there's some probability I would do that right now. So I can then use that in a likelihood function and put these discrete choice probabilities in with parameters in the utility function, and maybe I want to estimate the sigma parameter. In some conditions, I can do that. There's a issue of identification, and I just take this is the likelihood. I take the log likelihood, and I maximize that. And it's beautiful when this is linear parameters. In many cases, where it's kind of xd times theta. This will be globally concave. You can use concave optimization. So it's almost like doing a regression. So doing low bits on a computer in a lot of packages like Stata is really, really easy for very large numbers of alternatives. Okay, I'm going to stop there and now switch to, I'm going to skip over a bunch of slides. I was talking about Potts-Miller inversion. I won't have time to do that, but others will be able to come back to that. And I want to talk, but by the way, here's Dan McFadden. Here he is, my thesis advisor. Great. I was very lucky to have him. Now I want to go to our people Bayesian. Let's take and I want to contrast what they do, how they get errors in the model with what we do. Okay, so I put this in the book. It's a 1995 Journal of the American Statistical Association, and they did an experiment on 257 college students in California. And here's the way the experiment was done. There's 2 bingo cages, and they had 6 balls in them. Okay, so one cage, and the balls are marked N and G. They have letters on them, N and G. And one cage has 3 N balls and 3 G balls, and the other has 4 N balls and 2 G balls. And what's going to happen is you have this desk up here, and they're going to pick. You're going to see that these cages have these balls in them, and then they'll kind of put a little curtain over it, and then you won't be able to see which one they're choosing, but they're going to draw 6 balls with replacements. So they'll show the ball that they got, is it an N or a G, put it in front of all the subjects, then replace the ball, spin the cage again, draw another one, so you won't know which cage to draw, and you'll get a sample of 6 balls drawn with replacement from one of the cages. And the subject's job is to predict which cage did the sample come from. Very simple. It's a simple binary discrete choice model. And furthermore, they had another cage with balls with just numbers 1 through 6. And then they gave them prior information. They said in the first experiment, if the number is between 1 and 3, we're going to choose cage A. If it's 4 through 6, it's going to be cage B. Now they don't show the number of the draw, but what they're trying to do is create common knowledge. There's a random procedure that with probability 1/2 you'll choose, that's a prior probability. The prior probability that you draw from cage A or B. And then and another one they said with probability 2/3 will draw from cage A. So there's 2 pieces of information that are going to come out of this experiment, right? First of all, you're told in common knowledge what the prior probability of choosing from cage A, that your sample is going to, that's prior. And then you get posterior information, how many balls in the sample with replacement are going to be marked capital N. Okay. So now if we're going to do this with Bayes' rule, first of all, we write down the likelihood function, right? There's a probability of A. Well, A has the 4 N balls, so it's got a 2/3 probability of drawing an N ball from cage A. And if you're drawing from cage B, there's equal number of N and G. So there's a 50-50 chance. So these are the things that if you did elementary probability theory, say, yeah, these are binomial probabilities. Just the total number of N is sufficient. We don't, because they're IID, the order doesn't matter. We just don't know the number of balls. Little n is the number of balls marked big N. Okay, you follow that? And so the person will observe N, but at the start of the experiment, they're informed about what the prior is. Okay, in the common knowledge way. Now, here's Bayes' rule. Bayes' rule is you form the posterior probability. Now, it depends really on pi. I didn't put that explicitly in the notation, but it's the posterior probability of given your prior and given n. Now you reverse this. Before we had probably had given a, but we don't know if it's a or b. So then given n and pi, this is the posterior belief that we think is from earn a. Now, if you're a Bayesian decision maker, what should you do? If you're rewarded, you're going to be rewarded on choosing the right earn, then naturally you should say, if my posterior probability is more likely from earn A, I'm going to choose earn A. If it's less than 1/2 probability, I'll choose earn B. Right? So you just calculate this thing and then look whether it's bigger than 1/2. If bigger than 1/2, you say A, less than 1/2, you say B. Okay. Now, here's something that's an exercise. You can prove this. If you are a decision maker, we can think of a decision rule here is a delta, is any function of n and pi. This is a particular one called Bayes' rule. Is Bayesian the best? And the answer is yes. If you are a decision maker and you're rewarded, you get more reward for picking the right case than the wrong case, the way that you maximize your expected utility is to follow that Bayes rule right there. That's the optimal way to do the decision making. So that's a kind of exercise in the law of iterated expectations. I can provide a proof to you, but it might be worth trying to go home and say, how do you do that? How do you show this optimal decision making? Now, you can translate that into something called a cutoff rule. The probability that A is bigger than 1/2, you can reframe that as there's a cutoff that depends on the prior, that if you have more than some integer number of walls, that should cut off. And that's what they focused on. They said, let's just retranslate it into cutoff rules. And if you have 3 priors, there's going to be 3 different cutoffs. And so Bayes' rule would be cut off when the prior is only 1/3. You need more evidence. If you have more than 4 walls in your sample marked n, then you say A. If you have a 50-50 prior, you need a little bit less evidence. If you have more than 3 walls marked in, you'll say A. And if it's a 2/3 prior, all you need anything more than 2 walls, you'll say A. But they said maybe these subjects are using cutoffs that are not Bayes' rule. So any integer, any 3 integers could be a cutoff. So they're going to say we're going to restrict. So if you look at all possible decision rules, there's 7 possible values for n and 3 possible priors. That's 21 possible. And since you make 2 decisions, there's 2 to the 21. There's 2 million possible discrete decision rules you could use. But when you restrict the cutoff rules, there's actually only 8 to the 3rd possible. There's 8 possible cutoffs from -1 to 6, or 512. So they're going to say we're going to estimate these cutoff rules, and now they're going to say though, we will not always follow any given cutoff rule. So in other words, if you don't have an epsilon in the model, it's going to be statistically degenerate. So what do? They're going to assume that there's a tremble. So in excess, the number of trials that are consistent with using any given cutoff rule is E. It's a triple of these cutoffs. And then there's other trials that are not consistent. You could have been using that cutoff rule. So they're going to say, hey, there's a probability epsilon where I either follow the cutoff rule, or if not, I just guess at random. I just say A or B, 50-50. Okay, so for some reason, it's just like your brain state, you're good at following the cutoff rule, but sometimes you're distracted and you don't. And that means that the probability of following the rule is actually 1/epsilon/2. Because why? You could have chosen the correct follow your cutoff rule, but by guessing, right? You could with some probability epsilon guess, but then I choose to follow the cutoff rule. So that's why it's 1/epsilon/2. So I either make it consistent with the cutoff of this probability, or I do something else with this probability. So now the parameters are epsilon and c, and you can write down the likelihood. And now this thing is non-degenerate. Okay. And basically what they found is they estimated this model. So what they used is something called the estimation classification rule, but it allows for heterogeneity. So let me go back here. Sorry. If you use only one type, if you only allow one cutoff rule and a common error rate, they found that the cutoff rule, the maximize the likelihood, is Bayes' rule, 4-3-2. Okay, and so if they say, are people Bayesian? If you're restricted to only one rule, yes, people are Bayesian, but with a very big error rate, it's like 15%. 15% of the time, you just guessed it. Now, then they allow heterogeneity. You think about this doing it like subject by subject. You could use formula like there's enough trials where you could estimate subject-specific cutoff rules and error rates. And then what you find is there's other behavioral ones like representative, like if the sample is 50-50, you say, well, that's like R&B, but you ignore the prior. So if the prior is 2/3, you're going to do A, and the sample happens to be 50-50, you shouldn't pick R&B. You should actually, the weight you have to consider the prior. So you're downweighting the prior. Okay. Now I'm gonna, how much time? I'm a little bit over when I get through this. Can I just go through, finish this up, and then I'll let you get some coffee. Now let's do it McFadden's way. I'm a student of McFadden. Not that I'm trying to, but I'm saying, here's what I would do if I was McFadden or me. This is how I would look at it. You're getting a reward if you pick the right page. Now I'm going to say, suppose you have a subjective prior. That's a subjective probability here of if you subjective probability, you see this data here, and there's some parameters in your subjective, not your prior, but your posterior. It's a subjective belief. I'm going to estimate that belief. And then we say, this is my subjective posterior belief, and a reward, and I expect a risk, the risk neutral maximum. I get this expected reward. And now I have this. Here's my, what Vern calls a grading. There's the random thing that sometimes makes you deviate. That's the random utility on your model. And then if this is the expected utility for two beliefs, the probability of B times R plus another error term. Now, what's kind of cool here is when we do this, we get a logit and a logit. So, the first formula, this is again a multinomial logit. It's the reward for choosing A, the expected value is A and B, and you can reformulate that in here. It's the reward times 1 minus 2 times the subjective posterior. Now, how do we parameterize the subjective posterior? I'm going to choose this formula here. It's going to be a binomial logit, and this is the likelihood ratio, the likelihood of A versus B. These are the likelihoods. And then there's the prior odds, and we take the log. Now, you may say, how would you ever come up with that? The reason I came up with that is that I can restrict these parameters. When I restrict the parameters to 0, 1, 1, I get the exact Bayesian rule, the correct Bayes rule. But I get Bayes rule of a particular subcase. But I get a lot of other things. So I can get all sorts of beliefs as I allow these three parameters to vary over 3 space. So now I have just 3 parameters. I've got the sigma, that's kind of the error rate parameter. That was like an epsilon in their model that was a single. And I have beta 0, beta 1, and beta 2. So I'm not going to hold you up too long. Let me show you the results. Here's a graph. This is the stuff. This is for all of their subjects with just one. We don't restrict only one rule. So it's like in this model here, we can also allow the betas to be subject specific. But now, by the way, I want to show you something. The C parameter in their model is not a continuous thing. It's a discrete parameter. It's 512. So their model is that strange asymptotics. It's a combination of a continuous epsilon and then these discrete. This model is all the parameters are classical continuous parameters. Okay. Now, so we get the asymptotic are a little bit different, but let me show you the predictions of the model. Now, here's the posterior probability, the true posterior probability picking cage A. So if you're using Bayes' rule, then whenever this is even slightly over 1/2, you're going to say cage A, probably 1. If it's slightly less, you're going to say cage B. So if you're a perfect Bayesian, it's the blue dotted line. Now, what's the black line? The black line is the empirical frequency in the data. That's just a fraction of subjects. So when in experiments they ran where this posterior, the true posterior probability is very close to 0, subjects were then close to 0, but not exactly 0. And when it's very close to 1, it's not exactly 1, but it's pretty high, like 95%. Now here's Elgo model in record. What it is there is the green curve. So what they're saying is you perfectly switch. Because all of a sudden you're using the Bayes rule. So when you move data slightly higher, they are, if you're not guessing, you get it exactly right. So you have this discontinuity, but then because you guess with a 15% probability, that's the epsilon over 2 there, you get this flat line. Now, which line fits the data better? Their line or the black line is the data? Now, where's our model? That's the red line. This is the subjective. I'm saying like that fits the data a lot better. Okay, hooray from the data. But we find that the betas are not 0, 1, 1. They're a little off. So in other words, are people Bayesian? I come up to a different conclusion. No, they're not. And they're like kind of noisy, distorted, Bayesian. They don't have the exact Bayes rule. But what's really cool in our model is in the data around the point of indifference. See, in their model, there's a discontinuous jump, way to 50-50. That doesn't seem reasonable, right? When the posterior is about 50-50, you're really struggling, right? It's just about indifferent. And our model, our way of doing the errors captures that, because when you look at this choice probability here, when that's 50-50, 2 times 1/2 is 0. So it's 1 minus 1 is 0. This is going to be 1/2. The logic model says when you're, the posterior probability, your subjective posterior is close to 1/2. It's like you're flipping the coin. But when it's far away, it's either close to 0 or 1. Then you're very sure, and then you get the behavior that we get. But it falls away very much like the data. Okay, so end of story. I'll stop here.